Good morning, Algebra 1 students. This is Mrs. Anspaugh, and I'm not sure if I'm going to be back in time after Cole's procedure this morning at the dentist, so I wanted to make sure I had some video notes for you just in case I don't make it back in time. However, today we're going to be talking about the graphs of exponential functions in addition to the equations for exponential functions, and then also looking at some real life examples for exponential functions. So to start off with, if you'll write down the objective to graph exponential functions, and then we're going to start looking at y equals 2 to the power of x. Notice the exponent is actually the x variable, and that's what is going to determine that we're working with exponential functions. We're no longer looking at y equals mx plus b. We're looking at y equals a starting amount times the growth factor to a power of x. So let's look here. Again, if you have your calculators handy, it would be nice if you could plug this into your function or get a graph and plug this in. Remember, f of x is the same as y equals. And we're going to build our table here. You can use your calculator to do so because Control T will also get you your table function or table feature. So the input values that I'm going to be looking at are -2, -1, 0, 1, 2, 3, 4, and 5. And I gave you those to start with. So if I input a 2 for x, we're looking at 2 raised to the negative second power, and that's going to give us 1 over 2 squared. We know we invert this or make the reciprocal, or also 1 over. So if we plot this point, -2 comma 1/4, we're going to go to the left -2 and just barely up a quarter. So we're not very high off of the x-axis there. When we input a -1 in for x here, we're going to be looking at 2 to the negative first power, which is the same as 1 over 2 to the first, or 1 over 2. So we're going to actually graph the point -1 comma 1/2. If we input a 2, we know that anything to the 0 power is 2, is 1. And so our point that we're going to graph here is 0 comma 1. And notice that is our y-intercept. That's going to play a role here in our equation. If we put in a 1, 2 to the first power, we all know is just 2. So we're going to go over 1 up 2. You can start to see this take off a little bit here. If we put in a 2, 2 to the second power is 4. So we're going to go over 2 up 4. Put a point. If we input a 3, we're going to have 2 to the third power, which is 2 times 2 times 2, or 8. So we're going to go over 3 up 8 and put a point. If we input a 4, we get 2 to the fourth power, which is 2 times 2 times 2 times 2, which is 16. And we're going to go over 4 up 16. And I pretty much think that would be the last point we can actually graph on this grid, because if we input a 5, we get 32, and I don't think we have room to go over 5 up 32. So that particular point is off the grid. It still exists, but it is off the grid. So if we connect our points very carefully, you're going to see a curve to our line. This is not a linear function. This is an exponential function. And this is a growth pattern here because we started off slow and we grew quite rapidly here towards the end. And if you'll notice, the 2 to the power of x, that means that we're doubling each interval. And that is your first exponential graph, graphing exponential functions. Notice, if we test this using the vertical line test, it only touches 1 point at a time. In fact, I'll do that again so you can see that it's crossing only 1 point at a time. So we can say, yes, this is a function. Moving on to the standard form of the exponential equation. And again, it depends on what textbook you pick up, but I prefer this way of representing exponential equations because for so long we've been talking about y equals mx plus b, and b has always been our y-intercept. Well, it's the same if we use this formula here. Y equals b times g to the power of x. B is still our y-intercept, or our beginning point, and g stands for what is it growing by. So if we write down what each of these mean, B is our starting value, our starting amount, our beginning amount. G is considered our growth factor. And of course, X is just time. It could be weeks, hours, minutes, days, whatever it is that we're looking for in terms of number of periods. So one thing that you'll be able to recognize, if G is a number that's greater than 1, then you're going to have an increasing graph. And it's going to look like this. It starts off slow and increases rapidly. However, when G is less than 1 or greater than 0, so some decimal, some fraction in between 0 and 1, we're looking at a decreasing graph, which we'll later learn is called decay, exponential decay. But our graphs are going to start up here and decay or decrease rapidly. And that is one of the best slides to show exponential growth and exponential decay, knowing that our growth factor is either greater than 1 or in between 0 and 1. So let's take a look at this graph. And before we even plug this into our calculator, before we even start plotting our points, let's talk about the formula here. Y equals B times G to the power of X. So B would be my starting amount, which is at 10. So that should cross the y-axis at 10. So start picturing this in your mind. And this number is less than 1. So instead of increasing, this should be decreasing. So we can already picture it's going to cross at 10 and then start to decay as we draw our curve. So here we go. I give you the inputs, -2, -1, 0, 1, 2, 3, 4, and 5. And if we put in a -2 and we calculate this out, we get 15.6 or approximately 15.6. So that means I'm going to go over 2 to the left and up 15.6 and put a point. If I input a -1 for X and I calculate this out, I end up with approximately or equal to, 12.5. So I'm going to go over -1, up 12.5, put a point. If I input a 0, we know that any number to the 0 power will equal 1, and 10 times 1 is 10. So ding, 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 there is our beginning amount or our y-intercept. No different than if it was a linear function. If I input a 1 and I calculate this out, I get 8. So over 1, up 8. If I put in a 2 and I calculate this out for X here, I end up with equals 6.4. So this is my output, over 2, up 6.4. If I input a 3 and I calculate this out, I get approximately 5.1. So over 3, up 5.1. Be very accurate when you're graphing, please. And if I input a 4 and calculate this out, I get approximately 4.1. So over 4, up 4.1. And last input, 5, calculate this out, and you get approximately 3.3. So you can start to see this gradual decline here, but it's not linear, which means it's multiplying by 0.8 each interval. And so again, we see this nice curve here, not a very steep curve. However, you can test it out, see if it passes the vertical line test, and sure enough, it does. We can also see that 10 here is the y-intercept, or B is 10. And then we can also talk about our growth factor being 0.8, which is less than 1. So it means it's decaying or decreasing. And there is a great example of exponential decay. So again, back to our original here, just to talk about a few features on this graph. Y equals 2 to the power of X. We're looking at, technically there's a 1 in front of this. If we're talking about Y equals BG to the power of X, there's a 1 here. So if you don't see a number in front of the G, it's always going to be 1. And keep that in mind. If you don't see a beginning point, it's there, it's invisible, it's just the number 1. And so again, you can see that the y-intercept is 1. G is our growth rate, which means it's doubling. So it's an increasing exponential function or exponential growth. So again, before we take a look at the graph and the table of this function, y equals 5 times 1.2 to the power of x, we're looking at a starting amount of 5, a growth factor of 1.2. So we know it's growing because it's greater than 1. It's not quite doubling. It's just a little bit larger than 1. So it's going to look like it starts off pretty slow and doesn't increase very rapidly. So again, we're going to fill in our table here. B equals 5 is our y-intercept. G equals 1.2 is our growth factor. And so we can already see here what's going to happen in our table. If I input -2, what comes out is approximately 3.5. So to the left 2, up 3.5. If I input a -1, I get approximately 4.2. To the left 1, up 4.2. If I input a 0, I get out a 5, which is my y-intercept. I knew that was going to happen. If I input a 1, I get out a 6, over 1 up 6. If I input a 2, I get out approximately 7.2. If I input a 3, I get out approximately 8.6. If I input a 4, I get out approximately 10.4. You can see how this is graphing. And the last graph, the input is 5, the output is 12.4. So not a huge increase here, but you can actually see it's still got a curve shape to it. It's not a linear function. And again, we have arrows at both ends. The last one we're going to graph here is y equals 50 times 0.6 to the power of x. So if you're looking at the starting amount here, it's going to begin at 50. And we're going to decay because it's decreasing at a rate of 0.6. So it's less than 1, so we know it's decay. And again, if we fill in our graph here, we're looking at inputting a -2 for x, so I get out 138.9. So go over -2, up 138.9. If I input a -1, I get out an 83.3. If I input a 0, I get out right at 50, my y-intercept. If I input a 1, I get out 30, so over 1 up 30. If I input a 2, I get out an 18. If I input a 3, I get out approximately 10.8. If I input a 4, I get out approximately 6.5. And if I get out a 5, or put in a 5, I get out approximately 3.9. And remind you, anytime during this video, you can pause this. It's not meant to work at the same pace that I'm videotaping, so please feel free to pause this so you can plot your points accurately. And once again, draw your curve and you can see this exponential decay. Okay, last few items here I want to talk about. It says find the domain and range of the exponential functions below. So again, we're looking at this particular function here. We know that the domain, you can put in any number for x, whether it's positive or negative, so we can say it's all real numbers. But the range means what am I going to get out? Am I only going to get out positive real numbers? So what I suggest is you type this into your calculator, call up the table feature, and look at the inputs and the outputs, the x's and the f of x's. So you can look at the domain and the range. Number 2, notice there is a 1 here. We just don't see it. So it starts at 1 and decreases by 0.9. So if you'll notice here, our domain, I can put in any number for these, but I'm only going to get out positive real numbers. Number 3, this -32 just means it's crossing the y-axis at -32, but it's still growing, not very fast, at a rate of 1.04. So again, I can put in any real number for x for the domain, but what's going to come out are negative real numbers. And number 4, I can put in any real number for x, but I'm only going to get positive real. So if you have a negative starting amount, your range is going to be a negative answer. Okay, last but not least, what happens when I have a percentage involved in my function? And I'm going to pause the video to answer that telephone call, but I'll be right back. Okay, I'm back. Again, this is looking at an exponential growth equation, but instead of the g here, this 1 plus the percentage rate, this is an equation when we are working with percentage increases and or decreases. We're only looking at growth. So we substitute our g here for a 1 plus r because percents are already out of 100% or 1 whole. So again, when I start to look at t being number of time periods, b starting value, that doesn't change. I'm just replacing my g with a 1 plus r so that it correlates to a percentage. So here's a scenario. A colony of 10,000 ants increases by 15% each month. How many ants will be in the colony after 1 year? So we want to talk about 1 year being 12 months. We want to talk about 15% being written as a decimal, which would be 0.5. So if I plug this into my equation here, I'm going to have y equals b, which is my starting amount, times 1 plus my percentage written as a decimal to the power of t. And this is what my equation is going to look like. Y equals 10,000 times 1 plus 0.5 to the power of 12. And you can put that in your calculator and find